Welcome to this explainer. Today we're diving deep into the intricate engineering behind cable television and video monitors. We'll be breaking down some highly technical architectures, precise synchronization mechanics, and the complex signal processing that makes these localized and widespread networks physically and mathematically possible. It's a lot of ground to cover, so let's jump right in.
Here's our roadmap. We're going to tackle video monitor specs, CCTV block diagrams, sync and configurations, CCTV applications, cable TV processing, and wrap up with cable network architecture.
Section 1. Video Monitor Technical Specifications. Right off the bat, there's a massive systemic contrast between standard TV receivers and dedicated video monitors. While a typical TV operates on an RF modulated signal that's strictly capped at a 7 MHz bandwidth, a video monitor takes a direct baseband signal, usually 1 volt peak to peak, straight at its input. Because monitors push 8, 10, or even higher megahertz, the resolution ceiling is completely lifted. Plus, high-grade monitors use a tighter 90-degree deflection picture tube. That smaller angle, well, that is the absolute secret to achieving much better linearity, lesser geometrical distortion, and minimal defocusing at the corners when you compare it to a standard television. When we trace the physical hardware flow, starting right at the video and sync inputs, you'll see they are both precisely terminated with 75 ohm resistors. The signal punches through the preamplifier, gets a final boost in the video output amplifier, and directly drives the picture tube. Meanwhile, the sync data takes a totally separate route. It travels through the sync separator to control the vertical and horizontal oscillators, ultimately hitting the EHT transformer that powers the electron beam. It's a beautifully separated process. To really grasp the larger systems we're going to look at, we need to lock down these core definitions. The preamplifier grabs the weak incoming video signal and preps it. The output amplifier delivers the high-amplitude muscle required to actually control the intensity of the electron beam. And the sync separator, you can think of it as a precision filter. It explicitly strips the critical timing pulses away from the raw picture data.
Section 2. CCTV system block diagrams.
In a standard closed-circuit setup, a centralized video amplifier acts essentially as the hub, transmitting the composite video straight over coaxial cable. But the real engineering magic here revolves around generating the blanking and sync pulses. Blanking pulses are absolutely vital. They literally turn off the electron beam during retrace. This ensures you get a stable, flawlessly clean image on the display without seeing the beam's return path smeared across the screen. Now, you might be wondering, how does a localized system keep perfect time if it doesn't have a master broadcast tower to rely on? Well, it gets incredibly clever. For vertical timing, it taps directly into the standard 50 Hz mains supply frequency, running it through a wave-shaping circuit to trigger the vertical oscillator. For the horizontal timing, it utilizes a crystal-controlled, astable multi-vibrator. That component fires off a series of precise clock pulses to lock the entire timing sequence in flawlessly.
Section 3. CCTV synchronization and configurations.
When you scale up to multiple cameras covering different angles, they have to move in perfect lockstep. A common synchronous pulse generator, or SPG, feeds the exact same timing pulses simultaneously to every camera in the chain. And there's a golden rule for this layout. The line absolutely must end with a 75 ohm cable termination. If you don't terminate it properly, you'll get nasty signal reflections and interference, ruining the entire feed. Physically, you can deploy these networks in two very distinct ways. Self-contained units are exactly what they sound like, an all-in-one housing for the camera tube, video processing circuitry, and all the sync and blanking hardware. Remote units, however, separate things out. Only the camera tube sits at the physical site, while all the heavy processing gear lives comfortably in a central hub, linked back to the camera by specialized multi-core cables. Let's say you have one camera, but you need to feed that exact image to 4 monitors scattered far apart. You're going to run into signal attenuation, meaning signal loss. To compensate for this loss as the feed travels down those long cables, you have to insert an essential piece of hardware called a distribution amplifier. It perfectly branches the single input into 4 separate 75 ohm terminated outputs, restoring complete signal integrity across the board. Alternatively, if you have multiple cameras feeding a viewing station, but you only want to view one at a time, you'd use a selector switch. The absolutely critical engineering safeguard here is mandatory mechanical interlocking within the switch itself. This physical block ensures you literally cannot press more than one switch at a time. It completely prevents 2 separate camera signals from violently crashing into the same monitor all at once.
Section 4. Practical applications of CCTV.
These highly controlled video networks are everywhere, and for good reason.
In standard surveillance, they monitor banks, commercial hubs, and busy traffic junctions. In industry, they're a total game changer, allowing us to safely conduct remote inspections in extreme, hazardous environments, like directly viewing nuclear reactions. In education, they're used to beam intricate, high-stakes surgical operations live to large medical lecture halls. And of course, they are equally crucial out in aerospace and deep-sea oceanography.
Section 5. Cable TV Signal Processing. A cable television headend is honestly a marvel of sequential engineering. First, massive parabolic dishes pull in the broadcast signals from a low-noise area. Second, those signals are converted into intermediate frequency, or IF, carriers. Third, they undergo rigorous filtering and amplification. Fourth, automatic gain control steps in to perfectly level out the signal strength. And finally, the audio and video are recombined, mapped to their specific channels, and dispatched out over the physical network.
Following that exact signal from the dish antenna, it hits the channel to VHF converter, then sweeps straight through the IF filter and amplifier. The real secret weapon in this process is the feedback loop, the automatic gain control. This is an absolute necessity to ensure the video and sound IF signals hold a constant, optimal strength before they ever hit the channel converter and go out to the entire city. Section 6. Cable Network Distribution Architecture. Once processed, the signal finally hits the streets. It surges down massive primary trunk lines, splits off into secondary branch lines, and eventually trickles down into what we call the twigs, which are the final cables feeding directly into a subscriber's set-top box. Because of the immense physical distances covered here, multiple amplifier boxes are strictly required at every single split along the path to keep the signal alive. This anatomical hierarchy, trunks to branches to twigs, forms the absolute backbone of the distribution network. Because the signal suffers immense attenuation over these physical distances, those booster amplifiers we just talked about are not optional. They are required at each stage. Furthermore, head-end processors must convert all UHF channels to VHF for distribution. Why? Because UHF signals possess much smaller wavelengths, making them highly susceptible to physical obstacles, which causes far greater signal loss over distance compared to VHF. I want to leave you with a provocative engineering reality to think about. We've seen how attenuation demands the constant insertion of booster and distribution amplifiers across the entire network to combat signal loss. But amplifiers don't just boost the video signal, they boost the underlying noise too. So at what precise point does that cumulative signal-to-noise degradation fundamentally, mathematically, break an analog cable network's physical ability to expand? Keep that hardware limitation in mind as you look toward modern digital solutions. Thanks so much for joining me for this explainer.